Oh, God. Nobody else is out sick. Okay, so our random variables and our probability distributions, we're going to look at them mostly in a table form. Again, we go back to the vocabulary that we learned at the beginning of the course: discrete, random variable, continuous random variable. What is the difference between discrete and continuous? Somebody give me examples. The discrete I can count. There's not a half of one. But continuous means there's lots of little things in between 1 and 2. 1.6775 or 4, 3, etc. Okay? So discrete and continuous. No gaps, no interruptions. So here's the key thing that we need to first check to see that I do have a probability distribution. There's 3 requirements to that. First, is it a numerical random variable? Is it numerical? We'll have some that aren't numerical, and we'll say, hey, that doesn't meet the requirements. The sum of all the probabilities, when you look at those tables, the sum of all the probabilities have to sum to 1. If they don't sum to 1, it's not a probability distribution. The thing that I will caution you is that when you're summing and there's a lot and there's maybe to 3 or 4 decimal points, remember we round, right? And if we round, sometimes it's not going to be perfectly 1. It may come out to 0.999. And that's still okay. It could be off that much, in other words, just due to rounding. Here again, we already know this is true. Any individual probability has to be between 0 and 1. So a lot of those things we already know. Here could be a graph or a histogram. It shows the probability here instead of the frequency. The probability instead of the frequency. So here's our formulas. Now, we are going to do these on a calculator, so you don't have to memorize the formulas. I know they just look awful, but they're not really that bad. Again, this means mu is our mean of our population, and we're going to sum, capital sigma. We're going to take all x datas times their probability of occurring. Okay? This, of course, is our variance. And then standard deviation is nothing more than the square root of the variance. So make sure you realize this. That the standard deviation is nothing more than the square root of the variance. The standard deviation is nothing more than the square root of the variance. Because when we look at these problems on our calculator and we get those statistics, sometimes our calculator is only going to give us the standard deviation. It may not give us the variance. So how would you get the variance? You would take the standard deviation and square it. Okay? So know that might happen. Okay, so first we're going to look at these and we're going to decide if these are discrete random variables, continuous random variable, or not a random variable. So taking a look at the first one. The first one is what? Is it continuous? Is it discrete? What's your thought? Exact weights of quarters now in circulation in the United States. Would it be random? It could be random, but is it continuous or discrete? Continuous, yeah. Continuous, because as much as we want it to be the exact thing every time they make one mint 1/4, it's not necessarily. Okay? How about the next one? It's discrete. Very good. Discrete, because I can count, can I? The number of tosses to get heads. Then when I look at the next one, C, responses to the survey. Did you smoke at least one cigarette in the last week? Am I measuring anything that's discrete? What's the answer to that question? Yes or no? Am I measuring anything numerical? No. So it's not a discrete. It's not. It's not a random variable at all. Now, had I said the weights of a cigarette would be what? Continuous random variable, because the weights are going to vary just a little teeny bit. You know, there's little plus and minuses there, right? Okay. But this sentence has nothing to do with numerics. So it is not a random variable. Not a random variable. Anything that's not a number is going to be not a random variable. Okay? So D says numbers of spins of roulette wheels required to get the number 7. Discrete continuous, yes. Discrete random variable. Because I can literally count how many spins it takes for me to spin that roulette wheel until I hit number 7. I could be there a long time. 1 in 38 chance. How about E, the exact foot lengths of humans? Continuous random variable. How about F, shoe sizes? It has to be continuous because it even says they're 8.5, right? Okay. How about number 6A, eye colors of humans on commercial aircraft flights? Yeah, it's not a random variable. Not a random variable. Good. How about 6B? Weights of humans on commercial aircraft flights. Continuous. Excellent. Number of passengers. Discrete, because I can count how many passengers. We don't have a half of a passenger, right? And the number of randomly generated digits before getting the digit 3. Discrete. Political party affiliations of adults in the United States. Not a random variable. How about the next one? Exact costs of presidential campaigns. It is continuous. Good. It is continuous because we said exact. We're not going to round anything. It's not $1. It would never be $1. But it wouldn't be $1.58 would be exact, and that's certainly a lot of gap between the number 1 and the number 2. Correct? Excellent. Okay, so here we go. Here's identifying the probability distribution. What are the 3 things that we have to check for? 1, whether it's a random variable, which means it has to have something numerical in it, right? So it could be the number of students in the class, the heights of you in the class. So that's our first check. Our second check is that the sum of all the probabilities have to equal 1. They must sum to 1. That's the next check. And the third check is, are each individual probabilities between 0 and 1, and it could be 0 and could be 1, so inclusive. So first off, it says genetic disorder. 4 males with an X-linked genetic disorder have 1 child each. The random variable X is the number of children among the 4 who inherit the X-linked genetic disorder. Is that a continuous or discrete random variable? Discrete, yes, because it's counting the number of children. Okay? So it is a discrete. So we've met the first requirement. The second requirement says, does all the probabilities add to 1? Jackie says yes. She says she's added them all up and they sum to 1. Excellent. So it meets that. Then I'm going to look, does every probability between 0 and 1 inclusively? Yes. So it does meet that probability distribution. So let's just talk for a second what that chart is telling us. That chart says the 4 males with the X-linked genetic disorder have 1 child each. The random variable X is the number of children. This is the number of children among the 4 who inherit the X-linked gene disorder. So, for all 4 of those men to have 1 child each, and none of those 0 children have that genetic disorder, it has a 0.0625 probability. In other words, 6.25% chance. The probability that there's not at least, there's exactly 1 of those 4 children with that genetic disorder is 0.25 or 24%. For 2 of them, 37.5%. For 3 of them, 25%. And for all 4 of them, 6.25. When we think about this, and if we were going to graph this, and we put our probabilities, but notice how this graph is going to go. It's going to be what? What did we just study? It's going to be a normal curve, isn't it? It's going to end up being a normal curve. So 0, 1, 2, 3, and 4. And 4 is way down low. 0 is way down low. 1 is at 0.25. And 3 is at 0.25, right? And 2 is at 375. Look. There's our normal curve. That's our distribution. It's a very normal distribution in this case. It doesn't have to be a normal distribution, but in this case it is. Okay? So take a look at that one. I'll give you a second to think about it. Okay, so tell me what you're thinking. First, does it meet the first requirement? Is it a random variable? What is it? What is it we're measuring here? The number of girls that he has to approach. The number of girls. Can I count girls? So it will be discrete random variable. Yes. What a sad pickup line, huh? If I could rearrange the alphabet, I'd put U and I together. All right, so it is a discrete variable. The next requirement is that the probabilities sum to 1, so all those sum to 1. Do they sum to 1? No. So it's not a probability distribution, and that's all I have to do. Decide whether it is or is not. Okay?
So wait, do that word again?
Probability distribution.
Okay, this is not.
This is not a probability because it fell short of meeting those 3 requirements. It has to meet all 3 requirements. The third requirement was that each of the probabilities are between 0 and 1. Would it meet that requirement? Yes. But it fails on this requirement, so it is not a probability distribution. Okay? All 3 have to hold true. Okay, so take a look at this one. Fun ways to flirt. In a Microsoft Instant Messaging survey, respondents were asked to choose the most fun way to flirt, and the accompanying table is based on the results. Does it meet the requirements for a probability distribution? That was quick. You said no. Why? I agree. It's not a number. Yeah. This isn't a number. It's not numerical. It's not numerical.
So that's where I was getting confused. So basically, in order to see if it is numerical, if it's discrete or continuous, look at that section. I don't know that.
Yes. What am I measuring?
Okay.
What am I measuring? Okay? Email is not numerical. In person is not numerical. Can I count the number of people? Yes. But the category in person itself is not numerical. Okay? So we bring up a new vocabulary word here of expected value. The expected value is nothing other than the mean. That's the expected value. That's what that slide goes through and says. It's the same exact formula that we saw earlier for the mean. So, here we go. The following table describes the probability distribution for the number of girls in 2 births. Find the mean, the variance, and the standard deviation. And if we go back a few slides, we could, in fact, use all of those formulas. So, let's go forward, bring that up, and bring your calculators out. My machine is so slow. Okay. So, in our calculator, just like we have before, we're going to go to Stat, and we're going to edit, because I'm going to put my lists in just like I did before. So I'm going to edit. For L1, I'm going to put the actual the variable itself. So I'm going to put 0, 1, and 2. Then on L2, I'm going to put the probabilities associated with each. So 0.25, 0.5, and 0.25. Just like we did before. And just like we did before, just because it's probability, it doesn't change anything. We're going to go to Stat, go over to Calculate, and choose number 1, the variable stats. And those of you who have my calendar, list 1 is L1, I'm going to go down to frequency and put in L2. Those of you who have the previous version, yours comes up with variable stat 1 and then it just stops right there. You have to put in L1, comma, L2. And the reason we have to do that is because if not, it only counts L1. We have to tell it L1 and L2 so that it takes those probabilities into account, okay? And then those of you who put L1 and L2 in, you just hit enter. Those of you with mine, we're going to cursor down to calculate and go ahead and press enter. So here's what my screen tells me. And obviously I can find the mean. The mean is 1. The standard deviation is 0.707. And where would my variance be? I've got to have variance. So I can do that. I can go 0.707 and square that. And I'm going to get, when I round that, I'm going to end up getting 0.5. So I took 0.707. I could have drawn it out more characters if I wanted to. And I squared it. And that will give me the variance. The variance then, when I round that, is going to be 0.5. So we'll circle the mean, we'll circle the standard deviation, and to get the variance, I'm going to take, whoops, the standard deviation and square it. So in this case, it's going to be 707 squared, and I'm going to get 0.499, whatever, and we're going to round that to 0.50. So it's still a lot better than doing those whole entire formulas, right? Everybody cool on that? Okay, so here's where they did it all out using the formulas, and they got the exact same thing that we got on our calculator. Okay, so here we are, back to that rule of thumb with whether something is usual or unusual. And again, we're going to be using that those values should lie within 2 standard deviations of the mean. Okay? If they identify unusual values that are beyond the limits, they are not within 2 standard deviations from the mean. So going to our girls, number of girls. We found in the families of 2 children, the mean number of girls is 1.0. The standard deviation is 0.7. Use the values to decide the maximum and minimum of usual values for the number of girls. So we're going to do the mean plus 2 times the standard deviation, and you get, well, you can do that in your heads, right? What's 2 times 0.7? So 1.4 and 1 is, and I'm going to take the mean, and I'm going to subtract 2 times the standard deviation, and I'm going to get well, that's kind of silly, because I'm never going to have a negative 0.4 of a girl, and if I only have 2 children, can I ever have 2.4 girls? So that means that anything in my probability distribution is considered usual. Everything that we've got is considered usual. Having 2 children, getting 0 girls, 1 girl, or 2 girls is usual. Okay, that's what that means. Okay, so rare event rule. The probability of a particular event, such as a coin toss, 992 heads and 1,000 coin tosses. Sometimes you just have to make the assumption. Just use your gut. If I flipped a coin 1,000 times, would it be logical that I would get 992 heads? You'd want to check that coin out, right? Something's not fair about that coin. So sometimes you just have to identify unusual results using the assumption that it's probably not going to happen. Well, we put a rule on it where it's the probability is less than or equal to 0.05, usually high or usually low, that probability is lower than 0.05, which is 5%, right? 5% each way. And, I'll go back to say that again. I've seen students who know the rule, they're trying to apply the rule, and if I gave you a number of that probability, would that be unusual or usual? It is unusual. Because if I look at this, is it less than 0.05? Okay? Less than 0.05. Okay. So here we go into the whole probability distributions. So I can pull that up just a little bit so we can see the whole chart. Ooh, okay. I can pull it a little bit. We just barely make it on the board. So find the probability of getting exactly 8 girls and 10 births. This chart in 10 births shows me the number of the probability of getting 0 girls, 1 girl, 2 girls, all the way up to getting 10 girls out of 10 children. Okay? So the first one says find the probability of getting exactly 8 girls out of 10. Well, exactly 8 girls out of 10 would be 0.044. Everybody sees that, right? But the next one, and this is really reading. Find the probability of getting 8 or more girls in 10 births. So that means I'm going to have to add together the probabilities of 8 girls, 9 girls, and 10 girls. So I'm going to add 0.044 added to 0.010 added to 0.001. And I come up with 0.055. I thought that was too easy. So really it's just reading and then putting it all together. Which probability is relevant for determining whether 8 is an unusually high number of girls in 10 births? Part A or Part B? Which would be unusual? The answer you got in Part A or the answer you got in Part B? A. Part A. So it would be unusual to get exactly 8 girls in 10 births, but it would not be unusual to get 8 girls, 9 girls, or 10 girls in 10 births.
And we know that because of the 5%.
We know that because of the 5% rule, absolutely. Is 8 an unusually high number of births in girls in 10 births? Why or why not? No, because it's not 5%. Is 8 an unusually high number of girls in 10 births? Well, what is that? 0.044. So is that unusual? It is unusual. Why? Because of that. See, when I first read it, it depends on how you read that. If it's exactly 8, it is unusual. And when you read that, you could read that to mean, is 8 an unusually high number of girls to get in 10 births? Do they mean it could be 8 or more? If they mean 8 or more, then it would not be unusual. So, because they didn't say at least 8.
Now, when you say is 8, are we going to talk about adding all of 0 to 8 together for the Q of X?
No, because this is unusually high for getting 8 in 10 births. So 8 in 10. And what my question is it worded such that it's exactly 8 or to get at least 8? So in something like that, I think it would probably be clearer on a test and say exactly 8 or at least 8 so that it becomes very clear as to what I'm asking.
So the answer is yes or no?
Let's see what the book says, because I don't want to, what number was that? It says no. See, that's because of the way you read it and you interpret that question, because the probability of 8 or more girls is 0.055. It didn't say the word at least, but when I read that, I'm like, ooh, what does he really mean? And when it says it's usually a high number, it could be 8, it could be 9, it could be all 10. Yeah, see? It's really interpretation. It's really a reading thing and how you're interpreting it. I will try to be clearer on test questions, because I see that can be interpreted either way. And if you explain your why or why not, and your explanation is how that I can look at it that way too.
And just to clarify, so 5%, so if something is over the 5, that is considered
Usual.
If it's below, it's considered unusual.
Correct.
Okay.
If it's less than 5%, it is unusual. I think it says or equal to. Okay. So here's the next one. And I'm going to let you guys work on that for me. Okay, part A. Find the probability of getting exactly 3 cars that fail among the 6 cars. That would simply be 0.041. Okay, find the probability of getting 3 or more cars that fail among the 6 cars. So I'm going to add 0.041, 0.005, and what are these 0 plus means? Anybody know? It's weird, isn't it?
Well, the total came out to .998, so I would imagine that it's so small that it's past the 3 digits, so they just left it as a 0.
Perfect, perfect. So Donald said, he said, what happens if you do this and you get the actual probability? We know we got to round to 3 significant figures. This could be something like, when I round that, it's going to be 0, isn't it? But there's really a little something there. So that's what that 0 plus means. And down here, this one could be something like, it really is so close to 0. We know there might be a little teeny tiny bit out there, but when I round it, it's still going to be 0. That's what that 0 plus means. Okay? So in essence, I'm really adding 0.041 and 0.005 to get 0.046. Okay, which probability is relevant for determining whether 3 is an unusually high number of failures among 6 cars? If it's exactly 3, it would be A, but if it's the way you interpret it, 3 or more, it would be part B. The same thing, is 3 an unusually high number of failures? Is it unusual or usual? It's unusual. Unusual. Because .041, and even if I looked at .046, is less than .05. Less than 0.05. See, it depends upon, again, which way you interpret that. Are you determining whether 3 is an unusually high number? Well, could it be 3? Could it be 4? Could it be 5, 6? So it depends upon which way you're interpreting that. Yeah. Okay. That's all of section 5.2.